Is it hot in here?
I'm hot.
No.
That's just because I'm fat, though. So.
Take your sweatshirt off.
I'm hot because I'm good. No, you know how hard it is to take the sweatshirt off. Look at these things right here. Look at these. They like cinch to my skin.
So we're going to talk about projectile motion. Projectiles are anything that's like, we could have a horizontal projectile, like if something rolls off of the desk and then falls to the floor, that'd be a horizontal projectile. And then you can have a projectile at an angle, so like if you kick a ball and it comes, it makes like an arch. That would be a projectile. Yes. No. So suppose two coins fall off the table simultaneously. One coin falls straight downward, the other coin slides off the table horizontally and lands several meters from the base of the table. Which coin will strike the floor first?
The one that was dropped. Like if you just go like this with the coin, it's going to hit the ground first. Well, I don't know. If you take a coin and go like that.
Yeah.
No, it'll go farther out and won't hit the ground first. If you're taking a coin and flipping it off the desk, it's going to have more motion.
Push it off the desk versus dropping it from the same height.
Let's just do it right now.
Because they fall at the same acceleration.
Oh, they fall at the same acceleration.
What's the same acceleration?
What is the acceleration?
Gravity.
If I go like this and it falls versus if I go like this.
Is it
from the moment the coin leaves the table?
But it's also going to be falling
They would leave at the same time. Leave at the same time.
Yeah, somebody got quarters?
Because the vertical
Do
velocity
any of the
is like
coins
zero.
have backspin?
No.
Then they fall at the same.
I mean, tennis. Yeah, because tennis involves quarters.
Are they round quarters? Are they round quarters or like the weird ones with like a pentagon shape?
There's no quarter like that.
Yeah, there is.
Those 4 quarters.
Oh.
A quarter.
Yeah, they are.
Would your answer change if the second coin was moving so fast that it landed 50 meters from the base of the table?
Yes.
No.
Yes.
Oh my gosh, yeah.
No.
Yes.
It's like I got a blue rock shooter, right? So I got one. I'm going to throw it and it's going to go straight.
Uh-huh.
And I got one right here. I'm going to drop it. Boom. That's going to hit while that one's still going.
Yeah.
Okay,
Because it has initial.
but no, we're talking about a coin. And
Blue rock coin, something.
If
no.
I had a coin like this and went boom.
And then remember, everything in physics that we're talking about, we're in a vacuum. So the blue rock is air.
Vacuum thing. Okay, well, then in that world, everything makes sense. Just drop a baby in an elephant suit. Didn't mean that. Baby elephant
And a car.
Okay, so here are two.
Look at that
Balls.
fantastic
Here, yeah.
piece of equipment.
Yes, this is very nice. Well, come so you can see. Come over here. I'm gonna move this little pin, and it's gonna shoot. This pin's gonna go back and shoot the ball that. Oh no, the ball will go this way,
And the other ball will drop.
and this ball is going to get pushed that way. So and it won't hit that far. But that way they can stop it instead of it rolling all over. Okay? What's going to happen? Are they going to hit at the same time?
I don't know. No, I bet you the one that flies out doesn't hit.
No, they won't hit at the same time. No.
Ready?
Brandon, don't touch it.
Same time.
Nope.
Oh, it hit.
That one hit it earlier.
Well, that's because it hit the desk.
Well, same time. You were right then.
Wait, what?
Let's do it again.
Yeah, Jack.
It is.
Technically, you are right.
They have equal weight. These are equal in weight, equal in size.
It doesn't matter.
No, same time.
No, it wasn't.
Let's do it one more time.
Do you think you know physics?
Yeah, we're not in a vacuum right now.
These are heavy enough that air resistance shouldn't matter.
Yeah, Jack.
But what
To
about
very,
gravity?
it's a very small degree.
Jack. What if I add air resistance to the equation?
How does that
There's a
work?
hole.
Oh, it's gonna
So then when this pin goes in, it just
Yeah,
drops.
what if Jacob kicks a 50-yard field goal with it?
That's not horizontal.
What if Jacob kicks a 50-yard field
Okay,
goal
you
and
ready?
drop the ball?
Hopefully it doesn't hit the desk this time. Ow, it hit my finger.
Get it! Someone!
Those look like they hit at the same time.
Nope.
It is the same time.
But
Yeah,
this isn't a
it's
vacuum.
Your eyes
so-
are wrong, Chase.
The vacuum doesn't matter.
Yeah, it does.
Not with these.
We're not in a vacuum now,
If
are
it
we?
was a glider, it would matter.
Yes, if it's a glider, it would matter.
They're not gliders.
If they were ping pong balls, it might matter. They'd be really light. Okay.
I like ping pong.
Chase, you are wrong.
you see that picture of how to get energy for free?
Yes.
Wouldn't that work?
No.
Why would that not work?
Wait, what?
You get like a belt.
Okay, so here, a projectile. Chase.
And they go through a bottle.
Chase.
And the air makes them rise.
Okay, projectiles are objects that are launched into the air. So tennis balls, arrows, baseball, a wrestler. Jack just perked up with. But gravity affects the motion, and the path is parabolic if air resistance is ignored. So this path right here is with air resistance, so it shortens it, but it's not a complete parabola. No, that would be a free fall object, I would say. Yeah. So the path is shortened. So the components of projectile motion. Let's think about the forces. What's acting? Remington, face forward.
Remy, we're discussing a limited
I know.
But the balloon's on top.
Show him the diagram after
But the balloon's
class.
on top with like.
Oops.
That's like the one with the stupid candy bar. You can get unlimited chocolate. You like cut it certain ways and you have an extra one each time.
No, you just get
Okay, projectiles. Done with that. Okay, as the runner, so this is a long jumper, it looks like. As the runner launches herself, she has an initial velocity in the x and y direction because she has to move up and over, okay? She's moving in the x and y direction. Does that make sense?
Yes.
She's launching herself upward and she's going in the horizontal. So she has a certain angle here, and we're going to break that angle into its components, like we did with the motions that we already learned. We're going to have an x component and a y component. So you notice the notation here. We have Vx initial, so the x initial direction and the y initial direction. And you can find that based on we can find her, if we're given her initial speed, the initial speed at an angle, then we can find the x and the y initial speeds. Right here? Vxi. Or sometimes I don't know, I always learned a VIX, the initial velocity in the x, but either way. VI, which would be her initial velocity here. And y cosine, because it'd be the adjacent over hypotenuse.
So what's the second one? VX.
VYI equals VI times the sine of theta.
Oh, hey.
Oh.
Jack wasn't done. Neither was.
Okay, so it equals VI's on both of them?
Yes, VI. You're basing it off of this initial velocity at whatever angle they give us, at the angle theta. Why is it what? Because it goes from her center of mass, which is right there.
So VY initial is the Y. Initial is the Y. Then theta is that thing, and then that thing. Okay.
Can I switch it?
Yeah, sure.
Can I go fill up my water?
No.
I'm really thirsty.
After we're done.
Hey, Chase, I can sponge some water. Not.
Okay, horizontal. So let's look at each motion. So we have an X motion and we have a Y motion, right? X motion. Is there any forces moving that object after she leaves the ground, or after the ball left that little, I don't know what you would call that apparatus, but after it leaves that apparatus, is there any forces acting on it in this direction, in the horizontal direction? No. Since there's no forces acting on it, there's no acceleration in the horizontal direction. So the x component of the speed is the same when it leaves. Well, let's think of that apparatus. When it leaves the apparatus, right before it hit, it's the same. The x. Okay?
I don't understand what you're saying.
Constant speed in the horizontal direction
For what?
for the ball that got shot out.
That, how?
How?
I think we should test this
'Cause
together
this-
because no matter how much little air resistance there is in here, the one that just drops is going to hit first.
No, it doesn't.
Yes, it does.
But
In this
why
room it
is
will
the
because there's still
acceleration
is there air in this room?
Because not acceleration, it's not accelerating. The speed is constant.
I understand in the vacuum.
So it gives it an initial speed when it pushes it off, and then that speed never changes as it goes across in this direction, in the horizontal
In
direction.
a vacuum.
Right, and it's here. Well, there's
Yeah, but it's like.
very negligible
No,
here.
let's measure it, and I guarantee you the one that gets
Okay, and then how would the horizontal distance travel change with successive time intervals of 1 second?
The change would be because the floor isn't 100% level, and neither is the desk. So if you want to factor all that in, and the curve of the Earth too, so
Yeah,
you can do all
and that
that.
one would still win. You just proving my
Oh,
point,
look
Alex.
at Meyer. Always got something to say.
Well, the
So
evolution of
the-
floor would be a bigger factor than the others.
So the constant speed, since it's a constant speed, we can use Vx. Oh, they'd be equal. So the distance from here to here to here to here, all the horizontal distances would be equal. Now the vertical distance, as we can see, is not equal, right?
You're getting your horizontal.
Whenever you say bounce off me, it stinks to you.
No, horizontal, the distance from here to here, here to here, here to here, because if you drew lines through these, okay, they'd be the same.
That's the vertical. Okay. Well,
The horizontal distance from here to here,
You should just be smarter.
here to here, okay?
That would become a nice person.
But we can, Vx is constant, so we can use our equation, V equals x over t, since we have no acceleration, that original one, we can use Vix equals the distance divided by time.
What do you not understand?
The horizontal.
What about the vertical motion?
That's changing negative.
Yeah.
Right, because we have acceleration due to gravity, the force due to gravity working on it, and so it's accelerating downward. And it's just simple free fall. So all those free fall problems we did last chapter, we can apply that to just the vertical motion. So our acceleration is negative 9.81 meters per second squared, and so our velocity is changing. And so we can see at each second, the distance between the vertical is getting larger and larger. Now, these are all the same equations we learned last chapter, right? Yep. Because we're using, they just make it really confusing. They'd use VI, this is VF equals, we have to change it into the Y. Remember, okay, the equations you already wrote down, they were this, let's look. Wasn't it, was that cosine? No, that was sine. Isn't this the equation you wrote down earlier from the previous, like, 2 slides ago? Okay, so this is this equation. Let's look at this equation. Our equation was VF squared equals VI squared plus 2AD, or 2A delta X, right? That's the equation from last chapter. So we have VF. Now if we look at just the Y direction, we have VYF squared. VI squared, look, VI squared is, but we need to be in the Y direction. So the VYI is equal to VI times sine theta. So they plug that in here. That's where this comes from. Does everyone see that substitution? Because we could just change all this to just putting a Y here, right? VFY and VIY.
I just squared the initial velocity instead of theta. Squared both.
Right.
I just plugged them in.
Yes. So VYI squared is equal to VI squared times sine theta squared. So So they took this right here, plugged it in here. Does that make sense? And then plus 2a, and we use delta y because we're looking at the y direction, not the x direction. So they just changed this 2a delta y. So it's the same equation, they just substitute in the y direction parts. Same with all these equations. These are be the same. So this one would be, we had delta x equals VIT plus 1/2 AT squared. So we're looking at the y direction, so they just say delta y. VI, y is right here, so VI times sine theta times delta t equals plus 1/2. They put AY, meaning the acceleration in the y direction. That would be what? The negative 9.8 times delta t squared. So it's the same equations, they're just specifying for just the y direction. Yeah, let's see what this has to say.
Projectile motion described horizontal velocity. Both balls are released at the same time.
Okay. This is our little experiment.
Projectile motion describes the motion of objects that are in free fall but have an initial horizontal velocity. Both balls are released at the same time and fall with the same downward acceleration. The initial horizontal velocity of the yellow ball does not affect its vertical displacement. As the ball leaves the pitcher's hand, it has a constant horizontal velocity. The force of gravity acts on the ball and accelerates it downward, causing its vertical velocity to increase. The two motions cause the ball to move in a curved path, known as a parabola. Air resistance changes the path of a projectile. When traveling through Earth's atmosphere, the projectile's path is not a parabola.
There you go. That's what it says. So this is what we said where x is equal to Vx times t. Because what's our equation for constant velocity? For constant velocity, we have, right? That was our equation for constant velocity. Since in the x direction we're at a constant velocity, we can use this. But they just changed this to Vx because we're talking about the x direction times t across is equal to x. Same thing. And then we talked about all these. So if it falls from rest, the reason why you don't see any VI, because initial velocity would be 0. So they've taken out all the VIs. So like this one, VI, I guess I should put Y. VIY, though, in the Y direction, the initial velocity, since it's being dropped, would be 0, so we just take that out, that whole part. Same with, what was it, x equals VIT. So they just take this out because that's 0. So we're left with, and we're not talking about x, we're talking about Y direction, is equal to 1/2 AT squared. So you don't have to know a bunch of new equations. We're using the same equations, we're just have to split it into the x and y directions. So projectile motion is free fall with an initial horizontal speed. Vertical and horizontal motion are independent of each other, meaning the vertical motion, it's accelerating, horizontal does not, so they're independent. They don't depend on each other. Components are used to solve for vertical and horizontal quantities. And the time, since it hits, I mean, you can't separate the time and the distance that travels and the y in a certain time is the same as the time it takes to travel the x distance. So the same time is the same. How does it have an initial horizontal motion? Because if you're like pushing it off and it goes horizontally first, you're giving it an initial velocity.
I still don't get how horizontal does it.
Because there's no forces acting on it.
Air.
We're in a vacuum.
But you said the balls didn't.
Very negligible because they're so heavy and the surface area is very small. The larger the surface area and the lighter it is, the more effect you have of air resistance.
But it's still.
It's so small.
It's still
Significant figures,
And then the velocity at the peak of the parabola of the y direction is 0. Just like if you threw something up straight up and down, remember when it gets to the top, the y velocity would be 0 and then it's come down. Yes, it was. Okay. Oh, yep. Good. So let's try this problem. I don't know. Let's see how easy they make one. People in movies often jump from buildings into pools. If a person jumps horizontally by running straight off a rooftop from a height of 30 meters to a pool that's 5 meters from the building, with what initial speed must the person jump? Let's draw this. On these problems, I just like to draw a picture, label everything. So I'm going to get a new page here.
Well, I wanted to see.
You guys are going to have to tell me. What color of ink should I use?
Green.
Green.
How are we supposed to do it when we can't see the problem?
Dylan has problems. Hey, we all have
Can't
problems.
see. I wanted to draw on my own.
And
I
then
could draw.
here's the pool.
Here's the pool. Wait, how deep's the pool?
Wait, is the surface of the water 30
Yeah, how deep is the pool?
30 meters below?
Oh, it's only a 3/4 full. He's gonna hit the bottom really quick. Nah, I don't think so. If he lands flat on his stomach, he'll make it. Won't fall that far down.
Unless we're talking about a midget.
Just explode. If you're talking about a midget, man.
I don't think you can jump that high. Jimmy, think about your life.
Wait, and he's not jumping at all?
We want to get this way.
No, he just jumped straight up.
He's just running and jumping.
He's just
And then
running
he
and he
falls.
jumps straight up.
No, he's not jumping up.
He's just falling.
He's just running straight off.
So it's okay.
To make the problem easier.
It's not very.
So it said 30 was this? 30.
Figure the rotation of the Earth.
Oh, come on.
And then he'll have to be in
And then this distance right here was 5.
Is he jumping? Is he jumping with
And what was the question actually? How fast does he have to run off?
question.
So we want to know if it's a horizontal velocity, right? Because what's our initial velocity in the y direction here? 0. We already know Vyi is equal to 0. We know that.
We need to find the time it takes to fall.
Okay, because Vx, what is our equation for Vx? X over t, right? X over t. We know x. What's x? Okay, so we know x is equal to 5. We don't know t. How would we find t? We're going to have to use some of our y equations because,
Equals 5 because of the distance. Yes, you know.
right, this is our x
So
distance that he has to do.
5:30, we got a 30, 60, 90 triangle.
What else do we know in the direction in the y? What's a?
0 or negative.
Oh, what else do we know? What is this?
That's y.
That's
I
y.
said that already.
Oh, okay. I didn't hear you.
I'm sorry.
So we already know VIY y, and ay.
So we can go 5 squared.
So can we find t using that information?
Which one's t?
Time. And once we find this time, we can plug that into this equation.
What's that angle?
We don't need to use an angle this time.
You can use the triangle y thing equals half ay times the triangle of t squared.
Okay, so 30 equal to 1/2 times. Okay, if we put a negative sign in, that's fine. We'll get a negative y. What does that tell us? Downward. So I'm going to just leave out the negative right now. Is that okay? Does everyone follow that? Okay. I can't do that. Times, okay, now we need t squared.
Well, half of 9.8 is 4.4.
What? 4.9?
That's not the time.
Well, it's half. That's half.
Okay, and so t squared is equal to 4.9.
No.
4.9 times t squared equals 30.
Yeah.
So 30
Okay.
divided by 4.9 and square root that.
Yes.
Algebra.
I thought you were telling me time was 4.9.
No, I just did 4.9 in my head.
I don't either. Someone have a calculator?
I have 3.
I'll do it.
Actually 6 if you include all the stuff.
Alright.
I don't know what the answer's supposed to be.
Hey, he's making a difference in this world.
Yeah. Mr. doesn't believe in energy.
2.47.
Yes.
So we can plug this in up here. So Vx is equal to 5 meters over 2.47 seconds. So because the time to travel this distance is equal to the time to travel this distance. So Vx, what is it?
I don't have the resources.
Is that what they tell us the answer is?
They say the answer is 2 meters per second.
So 2.02 is pretty dang close.
Yep. We got it right. Do I need to go back to this? You guys get all your work written down?
And it's only meters per second because it's the velocity.
Right, we took x meters divided by time.
Meters. Okay.
Oh, wait. Can you go
I
back
feel
down?
like I understand.
To this?
Do you have a negative 9.8? Well, then we don't have that data. Hold on.
Because we're moving downward, so you'd want a negative 30 and a negative 9.8.
Oh,
If you use the negative acceleration. Right,
you can't take square root of.
right. So, because we're moving downward, so y would be negative. Because final would be, because delta y is final minus initial. And final would be 0 and initial is 30, so it'd be 0 minus 30. So we'd have negative 30, but we just took out the negatives. Now this time it's a projectile launched at an angle. So that was horizontally coming off. This one's launched at an angle.
We use the fun.
A golfer practices driving balls.
A golfer practices driving balls off a cliff and into the water below. The edge of the cliff is 15 meters above the water. Man, they made this one a little difficult right away. If the golf ball is launched at 51 meters, an angle of 15 degrees, how far does the ball travel horizontally before hitting the water?
You can do like 20 things that you change. I spelled all of them. So you said 15 could be like negative 15?
Because it's moving downward.
So it could be like this. 15 is
Oh,
right.
So, yeah, is it?
no.
Is he good?
Okay, let me draw this picture. Let me draw the picture because I don't.
So you go 15.
When I wake up, bad things happen.
Use the golf ball. So this, right, this angle is 15 degrees. This is what? Does it give us an X direction? Oh, we're trying to find this direction. What else does it give us? Let's look. 51 meters per second. Okay. So this would be, no, this would be this. That's the angle. The angled velocity is 51 meters per second. And that's all we got. So now what?
We know why.
Yeah, so why is
Let's write down a given.
Okay, let's write down our, we know y. We need x.
So x looks about 40. We know.
We know, okay, ay is equal to negative 9.8 meters per second squared. Okay, let's draw a triangle out of this.
It's not a straight line though.
why is it asking travel horizontally when it never really did? It actually went.
But it wants the horizontal distance, so we're going to have to split it.
Chain again.
That's not very straight. Hold on. How I have to draw straight lines is like this.
Your dog chases rocks into a field. Oh yeah. I said I was someone chases balls.
So that's what we know from that triangle, right?
Yo.
Yeah, this is 51 meters per second, or this magnitude.
So he's vaulting off a cliff?
Yeah, I don't know why.
Initial velocity and the displacement of negative 15.
This would be VIX, and this would be VIY.
Yeah.
We're looking for time.
Do you even need VIY? Because it's going to start going back down, isn't it?
Yeah, it will go back down.
Yeah, but do you need VIY? Initial velocity going upwards?
Mm-hmm. There's an initial upward.
Going at 15 degrees.
Right. If it was horizontal, then VYI would be 0.
Velocity for your triangle.
Mm-hmm.
It's hot in here. Look. Warm velocity is exterior.
Chase, take your sweatshirt off.
No, I can't.
So you use social color, right? You remind me of the dude.
Okay.
Yeah, I all know. I know that joke. That was a punch. It's really not that clever.
No,
Neither are you, apparently.
but it's kind of like the kid being really hot with a coat on in class.
Alex, look at this. I have the sleeves rolled up. I'm not gonna do
Oh, the sleeves.
Well, then you don't need to wave it in your face.
See, Alex
You
is
need to-
causing problems.
You need to write these down.
I have the notes in my thing.
I know, but this isn't in your notes.
That's what the homework's for, right?
But this helps you with the homework.
Okay.
Chase, you need to pass this class. I don't think that.
Alex,
Chase, I think you just
don't
screwed up.
understand how much I don't like to listen to you.
Years ago.
You gonna take this class to graduate too?
Yep.
No, I have to take this class to get
Is what? 49.
Why of all? This one's like really hard.
Miss Cleaver said I could do it. So if I fail, I'll blame you, Miss Cleaver.
Miss Fisher is like, don't.
So now what? Now what should we do?
What can you start?
I think it's easier if we split this into two different motions. So split it like right at the top, because we're finding time, right? We're going to try to find time. That's what we need. I would split this into two motions. I don't know. You're
Well, you need a total displacement of negative 15, and if you're going like 150 meters per second with a constant negative acceleration, you can find the total time, can't you?
what? How would you do it?
Because you need because your total displacement for y is negative 15. if you have a velocity of 51 and then acceleration.
But it goes above 15. We have this distance we don't know.
Yeah, but your final displacement will be negative 15.
Yes.
And then like you have an acceleration of negative 9.8.
So you'd use the same equation.
Yeah, except with negative.
So what's that sparkle now? Well, I'm thinking about how I'm going to prove Meyer on about perpetual motion. What's that? The energy thing?
So our final minus initial,
You can't have
delta,
an
so
energy,
V,
no matter how
oops.
you explain it.
You're trying to create perpetual motion.
It has been.
Yeah,
So we're saying we're going to take 0 minus 15.
Yeah.
Because you know how many hours it took for me to find that picture? Nobody's found it yet except me.
Then why is it on the internet?
Because the internet goblin put it up there.
So technically the goblin has seen it, right?
Yeah.
Oh, we can't use this. Wait, because we now have an initial y direction, right? Because remember our actual equation, y is equal to VIYT plus 1/2 AT squared. That was our initial equation. We took out VIY when it was coming off horizontally because VIY was 0. But now VIY is not 0, so we can't take that part out.
So let's
It's
go
not
back
0
to that
anymore.
triangle up top. Where do you go after that? Once you find VIX and VIY, what happens?
That's what we're going to try something.
Try what?
I would split it into two different motions. And we probably don't have time looking at the time. Do we? We probably don't have time. So we'll save this and we'll start here tomorrow.